In a previous video, we did sort of inverse transform method for the exponential distribution and then also for the Cauchy distribution. And so what I wanted to do was see if we could understand and visualize the inverse transform method. So we're going to do this in R, and code is something here I'm going to share with you for the visualization that we're doing here. So what I'm basically going to do is draw sort of the inverse transform methodology. So the first thing I do is I'm going to look at the exponential distribution and the inverse transform method for the exponential distribution. So the way the inverse transform method works is it looks, remember, at the CDF or the cumulative distribution function, and then it inverts the CDF. So the first thing I'll just do is draw the CDF of an exponential distribution. So the way to do that is first I create a grid of values on the support of my exponential, and those grid of values are x being the sequence from 0 to, let's say, 10, and I'm going to put 1,000 values on the grid. Okay, so I do that, and then on the x-axis I'll plot x, the value x, and on the y-axis I'm going to plot the p-exp, which is going to be the CDF function evaluated at this point. Now, at any point, if I'm using a function that you haven't seen before, you can just go to the console, type question mark and do p-exp, press enter, and if you have everything's installed properly, the help page should open up. So the help page for the exponential distribution opens up because exp indicates the exponential distribution. And the description here says that the density, distribution function, quantile function, and random generation for the exponential distribution with rate. That means actually we can generate random variables from exponential using REXP as it is. But of course, in this class, in this course, we are learning how to do that. So we'll avoid using this for the beginning of the course. But if I look at PEXP, this is exactly what calculates the distribution function. Okay, and so what I'm going to do is plot x on the x-axis and the CDF function on the corresponding y-axis. Okay, so when I do this, that's exactly what I get. On the x-axis, I just have the x. On the y-axis, because the support of the exponential starts from 0, my CDF value is exactly 0, and then I have a continuous function that basically almost has converged to 1 when it's reached 10, right? So around 10, it's really very difficult to get values past 10 for the exponential distribution. So on the x-axis is the CDF function, y-axis is x. Okay, but now what I'm going to do is I'm going to produce the inverse of the CDF. Now, the inverse of the CDF is something that I know just by the analytical formula that we did in the previous lecture video. And so on the x-axis now for the inverse CDF, I now have a sequence 0 to 1. So on the x-axis for the inverse CDF are 0 to 1, and the inverse CDF function is minus log 1 minus foo. So foo is just a sequence of numbers from 0 to 1, and inv.cdf is the inverse CDF function evaluated at all of those values between 0 and 1. Okay, and now I will plot the inverse CDF. Okay, so I get on the x-axis, I get f of x or f of u, right? Or f inverse of u, sorry. And on the y-axis, I just get u. Actually, that's incorrect. So on the y-axis is actually x, and there we go. And on the x-axis is f inverse of x. Yeah, okay. Right. So what I want to do, what do we do in ratio of, not ratio of uniforms, what do we do in inverse transform is we generate a random draw from 0, 1. That is going to be generated on the x-axis, and then we somehow map it to the y-axis. So this function that you see is the inverse CDF function that's taking a number 0, 1 and exporting or giving us the inverse CDF. Okay. Now what I'm going to do is I'm going to draw 10 random draws from exponential 1 using the inverse CDF algorithm. So n equals 10, I will get 10 draws, and then I will get the algorithm says get 10 draws, then draw get as many draws as you want, then draw uniform draws between 0 and 1. Now, we've learned pseudo random number generators for uniform draws, but we'll instead use R unif to do that. So U is equal to R unif N, which means it's going to get 10 draws from uniform 0, 1. So if I go to my console and type U, these are the random 10 draws that I have gotten. And then I will take these U's and I will put them in my inverse CDF function. Okay, and that's going to give me the actual draws from X, right? From the distribution of X. So the inverse CDF is minus log 1 minus U for this for this exponential distribution. And so X is then set to minus of log of 1 minus U. Okay. Okay. So this is already something that we've learned to do. But now can we visualize it? So what I'm going to do is now let's actually see the draws U, these U, what do they look like? Okay. So on this plot are now going to be all the 10 draws that I have drawn. So these 10 draws now, I have drawn vertical lines indicating that these are the 10 different draws that I have drawn on the x-axis. These are the uniform draws. And I have drawn vertical lines indicating that at this value of the random generator of the uniform draw, it goes up and maps to this CDF value. Okay, the inverse CDF value, sorry. Right? So now what you're going to see is I want to see, well, on these uniforms, what is the corresponding value of X does it map to, right? So what is the height? So it goes up to that height and then it's going to go and find that height. So again, on the x-axis, we have U's, and now on the y-axis, where these values have landed up, we have X's that have been mapped. Okay. All right. Hopefully that's making sense. Right? And now I just draw the points. Finally, when I've mapped them, those are my actual draws. So now I've plotted them in orange with the points function. Now these are the actual draws. So I draw the values on U on uniform 0, 1, and I get what they're going to map to in terms of the actual draws from the random variable from the distribution. Now you will see that to actually get values above 3 or above 4, that happens because of the shape of the inverse CDF function. It's going to happen really not with a high probability, because my uniform draw has to actually come, near where my cursor is, near this area, for it to be actually happen that it goes out in the tails, right? And this argument or this logic gets even more exaggerated as you get closer and closer to 1, right? And that's exactly what happens. So that means for this distribution, for this exponential 1 distribution, just by the shape of the CDF function or the inverse CDF function, I am getting that I will get a lot of the draws happening between basically 0 and 3. Right? So if I change the number of draws from n equals 10 to n equals 100 and repeat this process, now you'll see in more detail what's going on. Now we have so many, let me make that plot again. Now we have so many draws on the x-axis, right? The window between 0 and 1 is basically uniformly filled in by all the draws, right? But you'll see for so many of them, we're only going to go up until the value, basically 5, right? Even though I've gotten so close to 1, because of the shape of the inverse CDF, the value that is in the tails I can only get is 5. So the tails of the distribution are basically going to correspond to the tails of the getting closer to 1 in this particular case, right? And most of the values are going to be nicely on the x-axis. Most of the values, half of the values are going to be between 0 and a half. And you see that means half of the values are going to be between essentially 0 and a 1, right? So hopefully, that visualization is helpful. Now, we can repeat this exact same process for the Cauchy distribution as well. So for Cauchy, now the support is not just positive, it's also negative. And so what I do is I create a sequence of Cauchy sequence from -20 to 20. And then I plot x on the x-axis and pt x df equals 1, which means it takes a t distribution, the CDF of a t distribution with degrees of freedom 1, and that is just Cauchy. Okay, so t distribution with degrees of freedom 1 is just Cauchy, and p next to it in the function means that I'm trying to draw the CDF function. Okay, so when I try that, this is what the CDF function of the Cauchy distribution looks like. Right? So you can see here it's very close to 0, and then there's a very rapid increase in the CDF function, and then it slowly decreases down to 1, right? So really, really interestingly shaped. Now, I can also draw the inverse CDF function with the same logic because I've actually found what the inverse CDF is in the notes. Inverse CDF is tan pi of foo, here stands for the u, tan pi of u minus 0.5. So foo over here, I've taken sort of a sequence of values from 0 to 1. And I plot the inverse CDF, which basically looks like this, right? So it looks nice. And this is what the inverse CDF looks like. Now I repeat the same process. I get 100 draws, n equals 100. I get 100 uniform draws, okay? And now x is equal to tan of pi times u minus a half, right? That's exactly what my inverse transform methodology says. So I find that, right? Okay. So now x should be draws from the Cauchy distribution, and I can visualize it in the same way. So I'm going to make the segments on the x-axis. So over here, I get, these are all the uniform draws that I got that seem fairly randomly located on the x-axis between uniform 0 and 1. So no clear patterns. Yeah, there's a few points here just by random chance and so on, right? And I draw the segments up, and then I match the segments to the y-axis. But now here's what I noticed. Because of the shape of the inverse CDF function, even though my points are so nicely distributed on the x-axis, right, or the uniform points are so nicely distributed, you see that because of the shape of the inverse CDF function, all of these points are basically so close to each other around 0, right? They're so very close to each other around 0 that they're really, really, really symmetric around 0. Right? And so when you take all of those points and you actually finalize them, you get a lot of the points around 0. And then because it's a Cauchy distribution, it has fatter tails than the normal distribution. It also gets a few points on the other sides as well. Right? And again, it's because of the shape of the Cauchy CDF or inverse CDF that you get so many points around 0. Right? And so the shape of the inverse CDF is going to tell us exactly what kind of structure we're going to get when the uniform random variables are mapped to the corresponding x variables. So the orange dots are actually my random draws from the Cauchy distribution. Okay. So this was a little bit of a demonstration of the inverse transform function or the inverse transform algorithm and what really looks like. And we can do this really nicely for the continuous case. For the discrete case, it's not as nice, so I couldn't show that for you. But in the continuous case, because you can plot the inverse CDF, it actually hopefully gives us a little bit more intuition.